Hi everyone, I am Hugo Lefeuvre, second-year PhD student at the University of Manchester. I am going to present the result of my research on OS design over the past 2 years, or how I try to rethink the operating system for isolation flexibility. This project is called FlexOS. This is the result of a cooperation between the University of Manchester, Politehnica Bucharest, Lancaster University, KIT, and NEC Labs Europe. This is the full version of my talk. So if we take a look at current OS designs, it is quite clear that security or isolation strategies are typically fixed at design time. Let's take the example of a typical monolithic operating system, such as Linux. There is the user kernel separation and the process abstraction using the page table. This is quite set in stone. You can make similar observations for other OS designs, such as microkernels or single address space operating systems. And the result of this is a view of the operating system that does not work very well with modern trends like specialization or hardware heterogeneity. But for example, if you want to remove the user kernel separation, you might want to do that for performance reasons as part of the unikernel trend, but it would require major rewrites. Or what if you want to use cherry capabilities or memory protection keys instead of the page table? That's also very much in the spirit of the times, and most will agree with me that this is no simple task with major rewrites and maintenance ahead. What we are trying to do with FlexOS is to propose a different approach and decouple security or isolation mechanisms from the design of the operating system in the first place. Ideally, the goal is to be able to achieve a range of security/performance trade-offs instead of a single point in the design space. We aim to support a range of isolation mechanisms, hardware and software, and granularities. In essence, what we want to do is to specialize the operating system for security for given use cases. Other use cases that we envision for flexible isolation include, besides pure specialization, deployment to heterogeneous hardware. Here, we're envisioning to make use of each machine's or architecture's mechanisms optimally with minimal code changes. You could also envision quickly isolating vulnerable libraries. Let's say a vulnerability is found in one of the libraries you're using. You can quickly and easily apply a fine-grained protection to at least mitigate it while a patch is being developed. Finally, we envision to use FlexOS's flexibility to guarantee that the properties of certain verified or safe components hold while being mixed and matched with unsafe components. So now that I'm motivated for flexible isolation a little bit, let me try to summarize the spirit and the scope of this project in 4 simple points. So first, we focus on single-purpose appliances, such as cloud microservices. So no desktop operating system, no general-purpose operating system. And the point is that we're advocating for specialization of the operating system towards the application it's running. And that starts to make much less sense when several applications are running at the same time. Second, we advocate for a holistic approach to compartmentalization. So instead of considering only the application or only the kernel, we want to have everything on the balance to make the best choices performance and security-wise. Once again, we want to specialize. Fundamentally, what we do is embracing the library operating system philosophy. All system components are libraries, and all libraries should be equal before the hardware. Third, we want to abstract away the details of isolation mechanisms. The page table, intent memory protection keys, cherry, teas, they surely don't have the same guarantees, but conceptually, they have a lot in common, and we can unify them behind a common interface, the isolation mechanism abstraction. Finally, flexibility must not come into the way of performance. Can we achieve a new layer of abstraction at nearly zero cost? Now, all of this is theory, so let's take a look at the concrete stuff we built. Let's start with a 10,000 feet overview of FlexOS. So in our model, users come with a simple configuration file describing the system that they want to build. So selecting an application, libraries, boundaries, and safety mechanisms. Following this, the toolchain will select an isolation backend that is going to provide safety primitives for the system accordingly to what the user chose. Isolation backends can leverage software as well as hardware-based technologies such as MPK or VMs. Then the toolchain is going to automatically rewrite the application and libraries to match requested properties. Finally, with this backend and written libraries, the toolchain will generate an appropriate image. These points here might still be somewhat confusing for you, and that's where the new abstraction comes into play. So let me speak a little bit more about it. So as I was mentioning earlier, FlexOS embraces the philosophy of library operating systems, and so it's quite naturally that we based it on Unicraft. The gist of library operating systems like Unicraft is that they are composed of a set of fine-granular, independent libraries assembled together at compile time. In FlexOS, we take that idea and start considering these libraries as first finest unit of compartmentalization. They're great for that because they have naturally well-defined interfaces with a clear cut on shared data. What we fundamentally rethink, however, is how these libraries communicate. As part of a porting phase, we pre-compartmentalize them. Fundamentally, what we do is we modify them to replace the function calls that they're doing among themselves and their shared data by abstract construct. And this abstract construct, we call them gates and data sharing primitives, and we define them as part of the FlexOS API. We will see how to do that concretely in the next slide. Finally, at build time, and based on the user's input, these abstract constructs are replaced by the toolchain with a concrete implementation. For example, function calls for no isolation boundary, MPK, T-domain transitions, or even VM RBCs if you don't want to go crazy for adding layers of isolation. So now let's take a closer look at the API. In this example, we consider a simple call to receive from the application implemented by the network stack. So here, as part of the porting process, we would first annotate shared data and add gate placeholders. Then, at build time, if the network stack and the application are placed in different compartments and MPK is used, we would replace the annotated shared data with a shared heap allocation, for example, and replace the gate placeholder with an MPK gate. That would, of course, be very different if we put the application and the network stack in the same compartment, in which case we would replace the annotated shared data with a simple stack allocation because we're in the same compartment, so no need to do anything in particular. And we would replace the gate placeholder with a simple function call because, once again, we're in the same compartment. So all of these replacements are performed with Coccinelle. I will not enter too much into backend details for time reasons, but there is more in the paper. So we built a prototype of FlexOS. The implementation, as mentioned earlier, is based on Unicraft. We have implemented backend implementations for Intel MPK and VMs. We have also ported libraries to work in isolation, the network stack, the scheduler, the file system, and the time subsystem. Finally, we have application support for Redis, Nginx, SQLite, and the iPerf server. In this talk, I will focus on demonstrating the flexibility and performance of FlexOS, but there are more results in the paper. So the first plot that we'll take a look at here is quite complex. So let me try to slowly introduce it. So what we want to do here is to demonstrate the flexibility of FlexOS, or the design space that we can achieve. So here we are measuring the performance of Redis in requests per second. At the bottom, you can see FlexOS libraries used in the Redis image. So of course, only a subset for readability. The Redis application, the C standard library, the FlexOS scheduler, and the network stack. The way to read this plot is that each bar represents one configuration and its associated performance. There are 80 configurations in total. At the bottom, you can see the compartment the library is in. So for example, white for compartment 1, red for compartment 2, etc. The dot indicates whether hardening, for example, the address sanitizer safe stack, is enabled for the said library. So the first observation that we can make here is that we have a pretty large gap between the most expensive and the least expensive configurations. And the configurations at the extremes are roughly what we would expect them to be, full on and full off. We can also see that the slope is pretty smooth. Basically, if you give me a performance price that you're ready to pay, I can give you a configuration that's pretty much exactly what you're asking for. The most interesting thing, however, is that you sometimes can get very different properties at pretty much the same cost. And most of the time, that's due to the way libraries communicate among each other. Take the example on the right. Security-wise, they are very different. On the left, you have 3 compartments, the network stack and the scheduler, 2 different compartments. And on the right, you have the network stack and the scheduler in the same compartment. Performance-wise, however, they're the same because in both cases, you have the same number of crossings. Unfortunately, the network stack communicates with the scheduler via a 3rd library that's always in the other compartment. So clearly, you can get some safety for free by exploring intelligently, and that's something we explore in greater detail in the paper and later in this talk. There would be more to tell, but I hope that I could give you an idea in this limited time of the interesting things that we can do with such flexibility. The second set of results we're going to take a look at is focused on performance in comparison with the baseline. Does flexibility come into the way of performance? So here we're looking at numbers on SQLite, namely the time to perform 10,000 SQLite insert queries in seconds. At the bottom, you can see the number of compartments and the mechanism used. For example, PT2 for 2 compartments with the page table. At the top, you can see the VMM of the environment. The measurement was done in. A first observation is that there is no overhead when disabling isolation. You only pay for what you get. So basically, FlexOS without isolation is Unicraft. That's a good step towards not getting into the way of performance. Second observation is that the MPK backend compares very positively to competing solutions. The comparison with CubicalOS is a little bit tricky because they're using LinuxU, a Linux user-learned debug platform of Unicraft. But if you look at relative numbers, it's still quite positive. And finally, the PT backend compares very positively to competing solutions, to equivalent solutions. Interestingly, we can see that we get almost the same number as Linux user-learned kernel situation, and that's because the cost of a transition between 2 FlexOS EPT VMs is similar to Linux user kernel transition. This is more clear in the paper. So now we've got this nice framework that allows us to easily build a large variety of images with a diversity of properties. In practice, this allows us to specialize the operating system from the ground up for a particular application. One difficulty, however, is that reasoning about such configurations is not entirely trivial. Some of them are not even comparable. Take this configuration, for example. Is the address sanitizer on LWIP and UKSCAD better than the address sanitizer on LWIP and SafeStack on Nginx? Well, not obvious at all. So we need to help the user a little bit. In order to do that, we propose a solution based on so-called partially ordered sets. Basically, if you look at the configuration space, you can see that while no total ordering exists, there is a partial ordering. This partial ordering is visualized here. Take this pair, for example. The ordering is clear. The address sanitizer on component A and B is better than the address sanitizer on A only. However, 2 configurations not on the same path will remain uncomparable. So now that we have this poset, we can start labeling nodes with performance characteristics such as throughput, or latency, depending on what you're interested in. In practice, as you will see shortly, we do not need to benchmark every configuration. Now, with this in hand and performance constraints, such as, for example, at most 30% of performance loss, we can output a set of optimal configurations for this budget. In practice, this corresponds to the maximal elements of the PO set, that is, the minimal set of unconfigurable configuration that satisfy the constraints. The user can then do the final choice himself. Since there is a strict ordering in terms of performance as well, no need to evaluate everything, and you can stop evaluating a path as soon as a threshold is reached. You could also devise smart search strategies like binary search. In the paper, we applied this to Redis and found it to be very practicable, reducing the configuration space from 80 to 5. So as a conclusion, we highlighted the need for more isolation flexibility, whether it is for specialization purposes to adapt to new hardware, or simply to quickly react to newly published vulnerabilities. Current approaches take one isolation approach at design time, effectively representing a single point in the design space. In this work, we proposed FlexOS, an OS that decouples isolation from the OS design, effectively making isolation decisions at build time. I presented some of our results and motivated automatic exploration of the new trade-off space. If you are interested in this work, you're more than welcome to come and have a chat. Good starting parts are the website, the paper, and of course, the source code. We're proud to say that this work is reproducible research. We worked really hard to make all results of the paper easily reproducible. A final big thanks goes to everyone who worked with me on this project, and in particular to the Unicraft community. And I would now be very happy to take questions.